get u times v equals, now this over here is u prime v plus integral v prime u. Do you see that? I split that now. Am I allowed to split that into two integrals? Yes, because there's addition, right? Addition you can split. You with me? What I'm going to do now, just tell me if this is algebraically correct or not. Algebraically, if this is over here, can I move it to the other side? Just like subtract it on both sides? Right? I could do that algebraically. So I'd have u times v, and then it would become minus, wouldn't it? And then u prime v plus, or not plus, equals integral, and then v prime u. Y'all still there? This is integration by parts. This is the formula. Now let me explain the formula, all right? Don't write this down as the master formula. Just hold on. I'm going to give you a master formula in a second. I'm just going to rewrite it. Let me write it like this. U times v prime equals u times v minus integral v u prime. All right, so this right here is this. Do you all agree? This, I just switched those. Multiplication you can flip. So that's that, right? Equals u times v minus, and then this is this one. I just flip those around. That okay? Look at what this formula is saying, or what this equation is stating to you. And I can remember Dr. Richardson, my professor, trying to illustrate to me, and I think he did a good job because I can still remember it, how the critical function of this equation. So over here in this integral, let's say this is the integral we're trying to work on, okay? What you see in this integral is a function, right? Times another function. But this function here is the derivative of something, all right? So let's say this is x, and let's say that this one is sine x. That was the one we were working on a second ago? Yes? So let's say that this is x, and this is sine x. We know that we can't do this, right? We've given up. According to this equation, this is equal to u times v. Now, do we know what u is? U is sine x, right? Do you know what v is? Well, this is v prime, right? So what's v? The antiderivative of this. Do we know the antiderivative of this? Negative cosine. Okay, so it's going to be x times negative cosine x minus, well, shit, we still have another integral to do, right? So why is this better? Why is it better? Well, check this out. What's v? If this is v prime, if that's v prime, then what's v over here? Negative cosine x. This is the key right here. If this was u, then what's over here in the new integral? 1, right? The derivative of u. And so this new integral is just going to have negative cosine x times 1, right? So the big key, and this is again what Richardson was telling me, is that what you do, the integration by parts formula does this. It takes an expression where you have something and its derivative, not the U substitution. These are completely separate from one another. It's a function and then the derivative of some other function, and it transfers the derivative. See how here there's no derivative on the U? See in the new one it is? And you see here the derivative is on the V, but in the new one the derivative is not on the V? They have switched places. You have transferred the derivative within the integral using this formula. Kind of make sense? Let's use this formula. I'm going to rewrite it one more time in a way that instead of writing v prime, I'm write dv. Is that all right? This means like the derivative of v, dv. u v minus integral v, and instead of writing u prime, I'm write du. So that's the same formula. Now the reason why I do this is because there's a cool little thing that you can memorize. It goes ultraviolet, oops, I should spell it right. Ultraviolet ultraviolet minus voodoo, V-O-O-D-O-O, voodoo, ultraviolet minus voodoo. It's just a catchy little phrase that you can memorize. And for some reason, it's easy to memorize, ultraviolet minus voodoo. Ultraviolet minus, now you have to remember the integral sign, but ultraviolet minus voodoo, voodoo, right, is the formula for integration by parts.
It's all clockwork orange.
It's like what?
Clockwork orange.
Sure. Yeah.
Never seen.
It's been too long. It's been too long. Do they? Is that in there? That's not the whole thing.
No.
Okay. Okay. All right, here we go. Let's see if we can do this. Now, if somebody ever holds you up in an alley, right, gunpoint, puts you up against a wall, it's like, tell me about integration by parts. Tell me, I want to know about integration by parts. It transfers the derivative, man. It transfers the derivative. Okay, that's the main thing you want to take away from it. It transfers the derivative. You have an integral, you know that's probably going to happen, you know, right? You're going to be walking down the average person is going to be, is want to know about integration by parts. Okay, back to this problem, right? Here we go. The formula, U dV equals ultraviolet minus integral voodoo. There we go. So what we need to do here, the way the integration by parts kind of works once you have a problem, is that you need to choose, you need to see two things. Okay, but they are not like something that's derivative. This is not U substitution. There are two things in the problem. You need to pick one of them to be U, and you need to pick the other one to be dV. One of these has to be U, one of them has to be dV. There's multiplication right here. So let's see, multiplication here. So I could actually pick my U to be the X, right? And my dV to be the sine X. But could I have done it the other way? Could I have let my U be the sine X and my dV the X? Yes, I could. So which one do you do? I'm going to just have you consider this. Please don't write this down right now. I want you to consider right now, if I let my U be X and my dV be sine X, I want you to compare that versus if I let my U be my sine X and my dV be my X. Okay, look at these. Right? I could go that's U, that's dV, or I could go that's U and that's dV. In the new integral, you're going to have v du, right? Okay, so if I look at this, du is going to be what, you said? Derivative of that is 1, and then v is the antiderivative of that, which is negative cosine, and that looks good, right? But look if you did it this way. What would du be? Cosine x, and what would v be? The antiderivative of this, which would be 1/2 x squared. So you're going to have cosine x and then a negative 1/2 or a 1/2 x squared in there. Do you really want to integrate 1/2 x squared times cosine x when you couldn't even integrate x sine x? No, right? So there is kind of a right and a wrong when it comes to what you pick, and you have to think that through. So you have to think about what the derivative is going to be over here. Make sense? Okay, so now, how do I do it? What is my method? The method that I like to show students is this. I always start these problems, integration by parts, with a table. I put U in the top left, and I put dV down here. Those are the two things I have to choose, right? Yes? I am going to choose X to be my U in this problem. And my dV is going to be the sine X, right? When you write that, though, put sine X and bring the dx with you, because we got to bring the whole thing. So this is our U, and this entire thing is our dV. All right with that? So do you agree right now? We have an integral U dV. All right? Now, I'm going to move straight down the table. Down is differentiation. So du, the derivative of u, is the derivative of x, which is dx. Do you agree? 1 dx. And then over here, I'm going to go up on the table, and when we go up, it's antiderivative. That makes sense? So this is going to be v up here. And what is the antiderivative of this? So do you realize what I'm asking you to do right now is this? Like you need to do like a little mental integral here to go from here to here, and you need to realize that that's negative cosine of x. Now don't worry about the plus c. We'll do a plus c at the very end. We'll put plus c, all right? So don't worry about it. Y'all good with that? Okay. Now let's do the formula, all right? So this is equal to what? According to the formula. U times v, right? U times v. Is this times this, right? Just, it's the x times that. No integral, right? Minus x cosine x. I put the negative out front in front of the x. And then I have minus now my integral. And then what is the next piece? V du, right? Which is this diagonal. It's these two across here, right? It's this one times this one. So it's negative cosine x dx. See, that's how I pick up that dx from that diagonal. And what about that negative out in front of the cosine? Can I just pop it out of the integral completely? Yeah, and that'll be a plus, won't it? So minus x cosine x plus integral cosine x dx. And what is the antiderivative of cosine x? Sine x. So we get negative x cosine x plus sine x, and then your plus c. That should be the antiderivative. What do you think? That seem weird? You'll get to do a lot more of this. I don't know. Someone was asking about differential equations. I plan on teaching differential equations soon, and I haven't taught it here, which is kind of strange, because a lot of times the class wouldn't make, but now a lot more students are taking it here before they're transferring out. Anyway, so I'm going through right now, and I'm doing all the solutions for all the homeworks. Like I'm just doing all the problems. It's taking me forever, but you don't understand like how much I use this in that differential equations class. I'm doing integration by parts. I mean, like on like 80% of the problems. Okay, good. All right, let's do another one. Oh, we never check the answer. We're not going to check them all the time, but can we convince ourselves that this is the answer? Let's see. Wouldn't that be a product rule? So derivative of this times this plus derivative of this times this, done with product rule, plus derivative of this. Okay, that's it, right? Cosine x cancels out with negative cosine x, and all you're left with is, well, those are both negative, so positive, so that's just x sine x. That's the original integrand. Yeah. So it worked. All right, what about this one? All right, let's first make sure we don't have anything else that's going to work, right? So like it's not a power of x, right? A basic substitution, what are you going to use? If you use a basic U sub, like you only have one choice. Natural log x, right? Really? And the derivative of that's 1 over x, and I don't see that here. Huh? So you really don't have any other options but integration by parts. So if I'm going to do integration by parts, my first step for integration by parts is to try and figure out these two things. I've got to pick a u and I've got to pick a dv. And again, I have very limited choices here. I really only have one option for u. What is it? ln x, right? Natural log of x. And my only option for dv then is 1 dx. But see, here's the beauty of the integration by parts. We're going to transfer the derivative. In my new integral, right? In my new integral, it'll be the derivative of this one, which is 1 over x, right? And in the new integral, it'll be the antiderivative of this one, which will be x. Okay, let's fill out the table. Down, du is 1 over x dx, and v is, what did you say the antiderivative of 1 dx was? X. So according to the integration by parts formula, we have what? U times v. What's u times v? Natural log x times x, which I'm going to write x natural log x, if that's okay. And then we have minus integral of v du, right? These diagonals multiplied. So x times 1 over x dx. And what happens to those x's? Cancel out. So you're just integrating 1. And what's the antiderivative of 1? Just x plus c. Right, so this right here is 1. Antiderivative of 1 is x. And we had a negative out there. So that's it. Now, look, if someone asks you what's the derivative of natural log x, everyone's like 1 over x, no problem. But what's the antiderivative of natural log x? X ln x minus x. All right? How would you check it? Product rule here. Derivative of the first one, 1 times natural log x, plus derivative of natural log of x, 1 over x, times the first one, x, and then minus derivative of x, which is 1. And see, this right here is 1. So 1 minus 1 is 0, and all you're left with is natural log x. So it works. I'm not sure the vibe I'm getting. I have a 1 o'clock class on Tuesdays and Thursdays. Same thing, Cal 2. And we didn't get to this in the other class, but I don't know. I just get this vibe from y'all that I don't know. It's hard to explain. It just seems like this is very uncomfortable for a lot of you. No? Is it just because it's the morning? I'm hoping it's just because it's the morning class. My afternoon class, everyone's like, yes, U is this. Yes, let's try this U. Everyone's like all wanting to give me their U's and let's do it and this is more like, man, this is going to suck. You know? It's like, it might be the morning, who knows? I hope that's, I'm miscalculating the morning. I'm hoping that's what it is.
Get a coffee pot in here?
I don't know. Maybe something. All right. So look, 10:19. So I accidentally scheduled an appointment at 10:30 today. I think I'm going to make them wait 5 minutes. So we're going to go for probably another 10 minutes, and then I'm going to give you a few problems to work on. And they're going to be it's going to be a quiz, but it's going to be a group quiz. All right? Y'all can work together. And what I want is when I give you the problems, whenever you're done, we're going to have one volunteer that's going to collect them at the end and then bring them to my office. So someone who has some time after this and is willing to earn some bonus points. See, there we go. There it is. There it is, right? So someone here? All right. We're going to have to do something fair. 1, 2, 3, 3. These three, we'll figure something out. Okay. But before I do that, in my notes for integration by parts, I have examples A, B, C, D, E, and F. And every one of these, I kind of describe what's going on here. So like in the first example, it's just a basic integration by parts. Second one is not so obvious. Third one is what we call repeated integration by parts. This one I call pulling a rabbit out of a hat because it's freaking magic the way this one works. And then this one we have to make a U substitution, a basic U substitution before we even start the integration by parts. And then this one we can actually create our own formula for sine to any power using integration by parts. So this is what we're going to do next class. It's going to be quite the journey through these problems. But let's try another, just kind of a basic U substitution. All right? Some people would consider this slightly torturing you, but I don't think it is. Doesn't this look extremely close to x sine x? Right? And the whole idea, close your eyes and envision this. We had x sine x, right? And in the new integral, what was our new integral in integration by parts? What happened to the x? It went away. The derivative, right? We took its derivative and it went away. Now we had to integrate sine to do that. And when we integrated sine, we got negative cosine. So we transferred the derivative and the power on x came down, didn't it? So wouldn't it make sense that if we did integration by parts on this, if we choose this to be u, right? Then when we go into the new formula, right, what's going to appear in the new formula if u is x cubed? It's going to be x squared, right? We're going to have a 3 out front, but it'll be x squared, right? And we'll have to integrate the cosine, which means in the new integral it's going to be sine, right? So the new integral will have x squared in it and sine. What if we do it again? So what if we do integration by parts again on that new integral? What would happen? We could pick the x squared as our u, pick the sine as our dv. In the new integral, it's going to be x and whatever, sine or cosine, one of them, right? And then what if we do it another time? Then we'll be able to take that x finally down to 1. Does that make sense? Like, if I choose this to be u and this to be dv, then in the integration by parts formula, in the new integral over here, the power in x is going to come down 1. And then cosine is going to integrate up to sine. Then if I do integration by parts again, the power is going to come down again, and then sine or cosine doesn't matter. And then again, and we can get it, and we can basically make that x cubed vanish eventually. Does that make sense? You sure that makes sense?
Yes, sir.
All right, that's your quiz problem. It's going to take 3 iterations of integration by parts. So let me just show you. I'll get the first one going for you. How about that? U and dv. What's u going to be? X cubed. What's dv going to be? Cosine x dx. Okay, let's complete the table. What's du? 3x squared dx, right? What's v? What's just sine x, right? Because we're doing antiderivative. That good? Yes? So according to integration by parts, what does this integral become? X cubed sine x, ultraviolet, minus integral, leave a little space after that minus sign, minus integral, these multiplied, right? So that's going to be 3x squared sine x dx. And can I pull the 3 out of the integral? Do y'all follow me to that? Okay. Now, what you need to do is you need to go and take that problem right there and go do that. Okay? All right? Go do that problem. And when you do that problem, you're going to have to do another integration by parts again. And it's going to split out, branch out again, yes.
What if it's like to the 200?
Oh, I would never do that to you.
Okay.
Yeah,
I didn't
no.
know if there's like a different way.
No, we would have probably what we call a reduction formula, Like if this was x to the n cosine, we would have a formula for that, which we could create ourselves, but I wouldn't do that to you. All right, so look, let's say you go and you get something here, right? You do all your integration by parts, and then within that one, you're going to have to do another integration by parts, right?
Yeah.
You're going to have to plug this answer back in here. And then you're going to have to take that answer and have to plug it back in here. And remember that negative 3 is going to have to distribute through to everything.
Yeah.
Have fun. You have 15 minutes. Yeah, do your own on your own paper. Everyone's going to turn in their own. At 10:40, I'll let you do it. Okay. I'll let you on the next time. Okay. So at 10:40, you're going to call time. All right. Everyone clear on this? At 10:40 time, because I can't let you stay longer only because people do have other classes after this, and it would be unfair. So at 10:40, we're going to call time. Everybody, what's your first name? John. Hand John your papers. Even if it's not finished, I just want to see what you've done. Okay? If you do not finish it, copy the problem down, take it home and finish it and bring it next time. All right? All right.
Once we get this answer, we can get one more time. Once we get that final answer,
Okay.
spend the last 20 minutes.
Okay.